Hello, good morning. Good morning, hello, can you hear me? I'm afraid I can't hear you.
Yes, we can hear.
Okay, great, great. We're starting in a few minutes shortly. Yes, thank you. Okay, hello once again. We are going to discuss some important topics today, and in particular correlation analysis, and then we'll proceed to simple form of machine learning, which can be used to construct continuous price prediction in our models. in general, it is not limited, definitely not limited to our market microstructure model. So the topics we are discussing today and generally from today on will be pretty much commonplace, general, applicable to multiple situations. Nevertheless, we'll be using examples from our familiar numerical setup in order to provide illustrations regarding our points. Okay, so a number of points to begin with. Uh, I received questions about our final exam. The final exam will be in the form of defending your project work done so far during the term. So it's definitely not that you are going to receive some specific new project to be done for the exam. It is just your labs and home assignments which you have been doing throughout the course. You will need to discuss, defend, answer questions, and so on. So I would like to make sure that this type of final exam is familiar, clear for you, and basically you know how to deal with it. Are there any questions about that?
Could I ask one more question, please, about the format? Could we, as students, come to the exam in online format as we do in the labs?
Sorry, your point is whether it will be in online format?
Yes, because some of students are not physically presented in Innopolis.
Well, if some students are physically not able to attend, then it is a very good idea to do it in the online format. Yes, why not? Actually. Do you have any idea actually how many students are physically not in? Because we can either do online for those who are not able to attend in person, or we can do it online for all. But in order to understand that, we need to get the number of how many students do you think are missing because they are locked out.
I believe it's better not to guessing, but maybe conduct a poll to find out which format will be appropriate for everyone.
Well, yes, please do so. Yes, okay. In general, I have nothing against the online format. It is perfectly okay to do so. Uh, our technical means like Zoom would perfectly allow us to do that. Okay, then we had a discussion last week, and in particular in your labs, about two things related to correlation analysis. One of them was construction of a correlation function and an autocorrelation function. And the other one was using the Hayashi-Yoshida correlation estimator in order to compute cross correlations between time series, and in those cross correlations trying to derive or infer lead lag relationships between the time series. I would like to dwell a little bit more on that. I think it is a good idea that you have started doing that and have probably read the paper by Hayashi and Yoshida. We, in our data science, data mining, any data related disciplines, should really rely upon current up-to-date papers containing important information. Unfortunately, not everything can come into a textbook, which we can always use for references. No, we really need to be able to read the papers and find the gist of information available in those papers. There are many things which are interesting and important, but they may be too much complicated, like proofs in that HY paper. But what is important for us is basically the essence of the method and how to use it and to which end we should use it. But first things first, we were doing a task on autocorrelation. Autocorrelation function. So, can you explain in simple terms, first of all, what we have been doing in the last lab about autocorrelation and what we got? So what kind of problem we are solving? Please tell me, so we'll be writing it down once again.
To see if the previous values we can predict or like affect the future prediction with the time interval.
We're using autocorrelation in order, you say, to predict the future. To some extent, that's valid. If there is absolutely no autocorrelation, like in the Brownian motion, then it is completely unpredictable and unknowable, as we have seen. But if there is an autocorrelation, then we can use this information to some extent for the prediction. So what our model was, we consider time instance like t0, and then possibly the previous ones, let's say t minus 1, t minus 2, and so on, t minus k, with the corresponding values of our stochastic process. So let's say the value is, suppose that this is the price. So for example, x I is the price of USD ruble, let's say tomorrow, at time ti, with the corresponding values x0, x minus 1, x minus 2, and so on, x minus k. Okay, do you remember what we did next? We have this time series. Okay, we are now here, but we have the previous values as well.
We calculated the differences between timestamps. For example, x1 minus x0, x2 minus x1 to find the intervals, the differences between interval when measure were done.
That's absolutely right. So what we did, we calculated the differences, which I would denote by delta x0, for example, which is x0 minus x minus 1, delta x1, which is, delta x in this case minus 1, which is x minus 1 minus x minus 2, and so on. And in general, delta x minus k, which is x minus k, minus yet the previous value, x minus k minus 1. So the first question is, why did we calculate the differences? Why was it so important actually that we do calculate the differences? So basically, we compute the autocorrelation function not between the values of x, but between the values of delta x. Not all the prices, let's say, but all the price increments. Why is that?
Maybe because the price change, like the new price depends on the price change, like based on the transactions, but the price itself is not heavily dependent by the transactions themselves?
Well, the reason is very simple. We take the differences, so these are first differences. For a very simple reason. You can only apply correlation analysis in general, autocorrelation analysis as we do, to a process which is stationary. What does it mean? So basically this is to achieve stationarity. We did not test it, but we'll see shortly how it could be done. Why that? So eventually, it is very simple. Eventually, what we would like to do is to compute the correlations. So basically what we need are the correlations between what we actually do. Delta x0, the latest increment, and delta x minus k, where k is 0, 1, and so on. Obviously, when k is 0, then the correlation is equal to 1. Or, without differences, correlation between x values themselves. x0, x minus k. So this is the right way of doing things. This is the wrong thing of doing our analysis. Why? Because typically this correlation between, let's say, x0 and previous values would, what does it mean the process is non-stationary? It means that this correlation would heavily depend on time. The correlations we estimate would depend on time somehow anyway, because these are just estimates. So we get effectively random values, and these random values, they do depend on the samples we are using. But conceptually, if the process is non-stationary, which means its distribution is different in different time cross-sections. So for example, the distribution of our process here at t0 is significantly different from the distribution of the process at t minus 2, and so on. So correlations between x values would in general depend on the choice of t0 due to non-stationarity. And that's what we don't want. There is absolutely no point in computing the correlation if it depends on a particular value of t0. Because you remember how we compute actually these correlations. We take our time series, then we apply a shift by k. You remember, right?
Yes.
Well, we center it, first of all. We apply the shift by k, and then we compute the covariance value over the whole shifted time series. And then we divide it by the quadratic variance. I will put the formulas once again for you to remember shortly underneath. But the idea is when we apply this k shift, it means that basically we apply the shift for the whole day. It would make absolutely no sense if correlations in different sections of this time series would be depending on the current time. If the correlations do not depend on time, then applying a uniform shift across the whole day is probably legitimate. If it does depend on time, then the situation is much worse. So before we can apply any type of correlation analysis, or indeed any type of statistical analysis on our stochastic process, we must make sure that the process is stationary. If it is not stationary, then there would be an implicit parameter T0, which is present in that case in all our computations. It is different in all different points of our time series, and it would affect the result. We simply have no way of getting a meaningful result in that case because we are looking for a constant correlation value, whereas in fact in different temporal cross sections we would have completely different values due to the explicit dependency on time. So this is of paramount importance. It must be absolutely clear, and there are a lot of serious statistical research activities in many fields of science done after the correlation analysis became popular in economics, econometrics, in biological sciences, everywhere. Then people started applying correlation analysis to address multiple problems, but in many cases they have forgotten about this stationarity requirement. And for that reason, they were getting, first of all, large, typically, and secondly, unreasonable, completely erroneous values of correlation. If, for example, if our process xi, suppose that our process xt is a Brownian motion. A very, very simple, let's say simplest model. We're considering the Brownian motion a little bit with you. Okay. So can you tell me, please, the Brownian motion, is it a stationary or non-stationary process?
Non-stationary.
Non-stationary. That's right. Why is it non-stationary?
Because there is a time axis. After some delta t, it changes.
Well, stationarity means what is a stationary process? Stationary means distribution of the process is identical in all time cross sections. What does it mean? It means if we have this Brownian motion we denote it by Wt. If we denote our Brownian motion by Wt and consider two cross sections WT1 and WT2, then there would be identical or non-identical distributions. But we know that distributions of Brownian motion, first of all, are non-identical because in general WT has a normal distribution, yet the mean is the same with zero mean, but the standard deviation of Brownian motion, you remember from our last lecture, is equal to what? Suppose
Square root of t.
Square root of t, yes. Square root of t. If we start from 0 at t0 equal to 0, we say it is 0 almost surely. It is sufficient for us to say that it is 0 with probability 1. Okay. So because the distributions do depend on time, then it is non-stationary anyway. We can make it stationary by considering the process, obviously, W over the square root of t, which has identical distribution, and 0, 1 for all t. This process is stationary. And if we construct this type of process, then we can apply correlation analysis like the shift we have applied so far, and we can compute the correlation between the process, between the process values. We can do it analytically as well. So the correlation between, suppose that there is a value s which is less than t, the correlation between ws and wt, do you know what actually the value of the correlation between these processes?
Maybe 0 because that's unpredictable.
It is not 0. That's an interesting thing. You remember from our construction of Brownian motion is that the increments of the Brownian motion are independent, but not the values themselves. So what we can write is that Wt is equal to Ws, because S is less than T. Well, okay, let's say less than equal to T. Plus the increment delta W between S and T. Okay? And this delta W between S and T, by construction of the Brownian motion of a random walk, you remember when we make a random walk, then it always has a normal distribution with zero mean and the standard deviation being the square root of t minus s. And also it is independent of ws. That's very important. So basically we have arrived at ws, and then we make yet another step between s and t, which is normally distributed, and moreover it is completely independent on the current value and where we are and all our previous history. That's very, very, very important, because all random variables in the left-hand side and in the right-hand side of our equation are normally distributed and have zero mean. So the mean is zero, okay? Then we can simply say, let us do the following. Let us multiply both the left-hand side and the right-hand side of this equation by, for example, WS, and take the expectation. So WT times WS equals to WS squared plus delta WST multiplied by WS. I simply multiplied the left-hand side and the right-hand side by WS. Now I apply the expected value operator. Expected value of WT WS. I do not subtract the mean because the mean is already zero. We know that all of them are zero mean. Equals to expected value of WS squared plus expected value of delta WST times WS. What is this value in the left-hand side? This is what we're looking for. It is not a correlation yet, it is a covariance between WS and WT. That's the covariance to be found. What is this value?
Squared expectation value of WS.
It is simply a variance of WS. And variance of WS is equal to what?
Square root of standard deviation.
The standard deviation is square root of S.
The square standard deviation.
Squared standard deviation, so it is a square root of S squared. Therefore, it is S. Variance of WS is simply S. And finally, what about this term? This term says that it is an expected value of delta WST, the increment, times WS. Because we know that these random variables are independent. That's very important. You can't do it in general. But by independence, it is equal
Professor,
to...
why we have the first term called the variance of WS? Because the variance is expected value of doubled WS minus expected value in square.
You are absolutely right. Variance of WS is the expected value of WS squared, you're absolutely right, minus expected value of WS squared. But we said all of them have zero mean. The expected value of WS by itself is zero.
Okay.
So in this case, they coincide. This is simply expected value of WS squared, which is equal to zero. That's true. And in the final term, by independence, we have expected value of WS of delta WST times WS. It is the product of expected values, but only by independence. Should they not be independent, we wouldn't be able to write that. Expected value of delta WST times expected value of WS. And the expected value actually of both of them, now taken independently, is zero. This is zero, and this is 0. So then obviously we get the expected value of, sorry, I can't move my screen. We get the expected value of both of them equal to 0, from which it follows immediately that the covariance of WSWT is equal to S. Why is it equal to S but not T? It is equal to the smallest value of time. So the precedence here that S is less than or equal to T is very important. We can only consider our Brownian motion as a process developing in forward time. So we have the value corresponding to the smallest value, smallest out of S and T, which is WS, plus this delta. We wouldn't be able to consider it in backward movement, like for example, it is WT and the increment going back from WT. Why not? Because in that case, we would lose this independence property. A Brownian motion has increments which are independent of the previous history, but not obviously of the future values, which means that we should consider only forward time in analyzing the Brownian motion. So it is equal to S, which is equal to the minimum of S and T. That's very important. In financial mathematics and econometrics literature, you can also, maybe you have seen it in other point in other cases as well. There is also a notation like that for the minimum. Have you seen that? This is nothing mysterious. It simply means the minimum of two values. Okay, that's what we got. We got the covariance between two Brownian motion values. And if we want to get correlation rather than covariance, how do we obtain correlation from that? So for covariance, we got it.
Dividing by variances of both of the random variables.
Standard deviations.
Standard deviation.
So correlation between WS and WT is the covariance between WS, WT divided by standard STD of WS and STD dev of WT. What that? This is S divided by, what is the standard deviation of WS? Square root of S. What is the standard deviation of WT? Square root of T. So basically we get square root of S and over T, which is obviously indeed less than or equal to 1, since S is less than or equal to T. Okay? So, if we, how would the plot look like? So it is a square root of S over T. If we consider our examples with T0, T minus 1, and so on once again, so that's the timeline. Here is T0, T minus 1, that's our notation, and so on, T minus K. Then, in case if it is a Brownian motion, what is the correlation between the Brownian motion at the point minus k, which is the Brownian motion at t minus k. I just use it to simplify notation. And let's say, okay, let's say t minus k. T minus k, sorry. T with a subscript of minus k. Let's use it that way. And the current T0. Now T0 is not equal to 0. 0 is somewhere here. Now it is other way around. And T current, T0. What is the correlation in this case? We denote the smallest value by S. So this is now S. And this is now T. Correct? Because we must have S less than or equal to T. And therefore, it is equal to the square root of T minus K divided by T0. Or if, let's say, we have a fixed time step tau, in reality, in your numerical experiments, the time step was not fixed because these were tick times, obviously separated by different time intervals. You remember that, okay? But for simplicity, suppose that we have a fixed time step. In this case, t minus k equals to t0 minus what?
Minus tau multiplied by k.
Yes, minus tau multiplied by k, assuming a fixed time step tau for simplicity. And therefore, that would be, in case of a fixed time step, would be equal to the square root of t0 minus tau k divided by t0. So it is the square root of 1 minus tau divided by t0 times k, where tau divided by t0 is probably some kind of small constant. So if you now plot this correlation as a function of k, k is non-negative. Minus k is obviously non-positive. So here k is greater than or equal to 0 because we put it minus k. So what would the plot be? So here is the correlation of w t minus k w t0 is a function of k. Okay, of k. And that's precisely the autocorrelation function of a kind you are trying to construct. So if k is 0, then obviously the correlation is 1. Right? It is a correlation of WT0 with itself, which is obviously 1. Now, as k tends to plus infinity, what will happen in this case with correlation? Effectively, it cannot go to plus infinity.
It tends to 0, no?
It will tend to 0. Moreover, at some point, you will get the value k so large that the argument under the square root becomes negative, but we can't consider those points. So obviously k is limited from above by the value of t0 over 2. That's obvious, because otherwise we would be crossing 0 and we would be before the origin of our time when our Brownian motion started. So Brownian motion started here. And here we're considering the correlations. But in general, it would be up to some k max. That's k max. It is parabolically decaying over time. Something like that. So, but that is the correlation function between Brownian motion values. That's very important. Can you do it numerically rather than analytically? Yes, you can. But in order to do it, you need first to construct correlation between stationary processes. So to do it numerically, just for you, this was analytical derivation, right? All right. So that's analytical formula. Just from the probability theory. How to get numerically? To get it numerically, you remember, you first need to do what? To ensure that your process is stationary. Make a stationary process. If you know that your process is a Brownian motion, then you can make it stationary by considering, instead of Wt, you consider Wt over the square root of t, which has n 0, 1 distribution for any t. All right?
Yes.
Then,
Could I ask a question about what is a square root of t in terms? So we should count from 0 as the start of the trading day. And
generally, yes. So the choice of the origin here is up to us. If we model our process as a Brownian motion, then yes, it is a very good idea to put 0 at the start of the trading day. In general, it is completely arbitrary. So for example, if you're only interested in your process within a particular hour, then you can put 0 at the beginning of the hour. But if eventually you remember what you do, you can construct the time series and then you apply a uniform shift across the whole time series, right? And therefore, yes, your 0 should be at the beginning of this time series, which you are going to shift eventually. So if you then apply your shift for the whole day, then t equal to 0 at the beginning of the day. If you only shift the data pattern to 1 hour, then you can put, if you like, 0 at the beginning of that hour. Something like that.
Okay, and time should be expressed in micro or milliseconds, depends on what unit we have, yes?
Oh, you know what? Generally, yes. But we discussed again in one of the previous lectures that it all depends on your scale, obviously. First of all, in reality, your process would not be a Brownian motion. Your process would be, it is a very, very simplistic model. In fact, your process would be a scaled Brownian motion, like something like sigma times Wt. I just put sigma equal to 1 in my case. And then the unit of time affects the value of sigma, actually. If you take your unit of time to be, let's say, 1 microsecond, suppose that, then you have a very, very small value of sigma. If your unit of time is 1 second, then you have a larger sigma. If your unit of time is 1 year, as normal in financial mathematics, then you would have larger value of sigma and so on. So basically, this is, by the way, scaled Brownian motion. Scaled Brownian motion. Unit of time, let's put it, it's a very good observation actually, unit of time affects the value of sigma. What I did in my example, I implicitly selected such a unit of time that sigma became 1. Just for the sake of simplicity. Select unit of time such that sigma becomes 1. What is this unit of time? I don't care at the moment, because my point is just to illustrate the method and contrast the method of finding a correlation function in the Brownian motion, or more generally in the price process itself, with the correlation function on the increments. That is very, 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 very important. So suppose that somehow we made a stationary process, or if xt is equal to sigma wt, where sigma is not equal to 1, then we construct this stationary process in the form of xt divided by sigma square root of t. So if sigma is not 1, we simply divide by sigma as well. And then we also get it stationary. Stationary with the distribution n 0, 1 everywhere. And then, since expected value of such a process, expected value of xt equals to 0, no centering is needed. You remember, in reality, you did centering. And you apply shifts by k or by tau k in time, and you get your correlation function. So in general, if you do it using your numerical samples of a Brownian motion, then you would get a roughly similar shapes of your correlation function as we did it in theory. So you would get your numerical result for a Brownian motion would be something like this. That's what you would get. More or less something like this. So this is a correlation function of a Brownian motion, or a scaled Brownian motion, or of a process similar to that. But that's one story. Another story is what if we take the differences? So this is a correlation between the Brownian motion values themselves. That's very, very important to understand. Let's move forward, sorry, backward. In the simplest case, and what we do here we compute correlations. So this is all about correlations between the Brownian motion values themselves. Okay. We could do it either analytically, or we could do it numerically if we assume that our process is a kind of Brownian motion by applying a similar technique with shifts as you have already implemented in your lab. So in that case, you would obtain a function like this. So again, these are correlations between the Brownian motion values. But at the same time, you can consider correlations between Brownian motion increments. And this will be a completely different story. Correlation between, why I'm using Brownian motion is because it is the simplest and the most easy to analyze a process which somehow represents a stochastic dynamics of, for example, prices or any other reasonable stochastic process. So we start with a Brownian motion. A real life process would of course be more complex than a Brownian motion. Now we say correlation between Brownian motion increments. Not values, but increments or deltas. Here we do it in a different way. Again, I'm switching back to blue. Again, we have the timeline, t0, and so on, t minus k. But now we consider deltas. Delta W, let's say between 0, suppose that this is t minus 1. This would be, I would denote it by delta W. Actually, it is between -1 and 0. Okay, let me denote it -1 and 0. Okay. This would be between, let's say, t minus 2, delta W between -2, -1, and so on. Okay. So here it would be a completely different story. Here we take this latest increment between t minus 1 and t0. So again, delta -1, 0 as delta at t0 minus delta at t minus 1. And in general, we consider delta W minus k minus k minus 1, which is w t minus k minus w at t minus k minus 1. K again is greater than 0. And I'm interested in correlation between this. So you should clearly understand this construction. We now take first differences, this point minus this minus this, and so on, and now construct the correlations not between the values of the Brownian motion, but between the corresponding deltas. So correlation between delta W between minus 1 and 0, and some more distant delta W between minus, if this is t minus k, this is t minus k minus 1. This is delta W between minus k minus 1. So delta W between minus k minus 1. Now, what is this correlation? From the theoretical standpoint, can you tell me, please, so what is the correlation between these two?
Zero.
Almost everywhere 0. It is 1 when k is equal to 0, obviously, and it is 0 otherwise. Okay? So it is something completely different compared to the correlation between compared to the correlations between your values of the Brownian motion. So again, if this is a function, this is a k, this is a correlation, it is 1 here, and at k equal to 0, and then it is 0, 0, 0, 0, okay, 1, 2, 3, and so on. So it is a completely different kind of correlation function. You remember, in that case, it was just gradually decaying to 0. Now we have 1 in just one place, and we have identical 0 otherwise. So the correlations between Brownian motion values themselves and Brownian motion increments are completely different. They look completely different. Again, this is from the theoretical point of view. How could you do it numerically? Numerically, you still need to make sure that your process is stationary. If all time intervals are of length tau, for example, for simplicity, assume that. If all of them are of length tau, by the way, that's what we did not do in constructing the correlation function when you did your lab. So the timestamps could be non-uniform in that case. But on the other hand, we didn't assume that it is a Brownian motion either. So as a very simple approximation, we didn't need to normalize the time intervals. But if in general t minus k minus t minus k minus 1 equals to tau, then we construct delta w minus k minus 1 divided by the square root of tau, and that has again, it is again stationary, it has n01 distribution, and then apply shifts. by k. Okay, now it comes to a practical result. We have considered a correlation function between Brownian motion values and between Brownian motion increments. Now, in reality, for your prices, you did correlation between price increments. In reality, we took price increments. Why we did increments? Because in general, we were lucky in the first example above. If our process was indeed a Brownian motion, and it is non-stationary, but we were lucky to know the distribution properties of this process. So we knew that if we divide it, for example, by the square root of t, then we would get a stationary process. But that's only if your process is zero. Is a Brownian motion. And by the way, what you also need to do in that case is to subtract the initial point, because by assumption, W0 at time equal to 0 must be 0. So in that case, you need to subtract the initial point as well. Otherwise, it is not a Brownian motion. It would be a shifted Brownian motion. But again, we applied our theoretical knowledge of our process being a Brownian motion, and then we knew how to normalize it. And then after normalization, for example, subtracting the initial point and dividing by the square root of t, we would say, yes, it has the N01 distribution in all temporal cross sections, and therefore we can now apply the shift technique to construct its correlation function. For real processes, we have absolutely no idea about that. Yet, it is an empirical fact that if a process xt is non-stationary, xt empirically xt is most likely non-stationary. But delta xt, first differences, is often stationary. That's why we apply the first differences. For the Brownian motion itself, as you see, we could achieve stationarity in both actually the process itself and in the first differences. In a real life process xt, we typically don't know how to achieve stationarity in xt itself, but in many cases, deltas of this process are stationary. So it is for that reason that we take price increments, deltas. Whereas for the original process, and we don't in general know how to make it stationary and analytically. Like, for example, dividing by the square root of t, we don't know. Because we don't know what we do, we take first increments and we assume that the process is stationary. Stationarity can be tested statistically. We didn't do it. There is a family of tests which you have probably seen, which are called unit root tests. Have you seen it in your course in mathematical statistics or anywhere? Unit root tests?
No.
No.
No. We will probably skip it for the moment because this statistical testing is quite an extensive, I would say, topic on its own.
But for what we should conduct this test?
We took the first differences of our process. We assume, because empirically it is often the case, that the deltas make a stationary process. X's themselves are not, but deltas are. But you see, we must not just assume. We need to verify it. You understand?
Yes.
So we need to verify statistically that the process is indeed stationary. So if it is indeed stationary, well, how can we verify it? And that's precisely how statistical unit root tests are what for. They are to make sure that we are really obtaining a stationary process. One of the famous tests to that end is a so-called Dickey-Fuller test, and many variants of it. I just make a pause maybe for 1 minute, and then we start from that point on. Okay. I'm not going into the details of how these tests work, but let me give you some example regarding this. So how can we distinguish between stationary and non-stationary processes? What are different types of behavior we can expect here? So suppose that we have a process in which I can put in a very simple autoregression form. So suppose that xt, simple model. Let's say simple model again. Suppose that xt is just a, some coefficient a1 times xt t minus tau. We have a fixed time step tau, for example, some coefficient a1 plus a Brownian motion increment, delta W, which corresponds to this interval between t minus tau and tau. For simplicity, I would denote this a random variable by epsilon, which has a normal distribution with zero mean and the standard deviation being the square root of tau. Something like this. Whereas we don't know actually anything about the coefficient A1. A1 can be just negative, positive, any value. Let me probably now construct the difference. Delta x t minus tau t, which I also just write as delta xt, which is xt minus tau, which is therefore a1 x t minus tau minus x t minus tau plus epsilon, which is a1 minus 1 x t minus tau plus epsilon. Or in differential form, replacing deltas with differences, we can write it as d xt equals to a1 minus 1 x. Now I write t instead of t minus tau, xt dt, for example, plus dwt. That's the same, effectively same story in a differential form. Taking tau to 0 as a limit, we would have it would of course be, let us put tau here. It's up to the coefficient a1 obviously. So in this case it is time tau, and then tau becomes dt. Sorry, just a second. 1 minute. So it is if I put it 1 minute, something is wrong here. If I put by default, I would assume in that case I would have a tau coefficient here in a1. No, that's not what I want. Sorry. I would put it that way. I would simply generalize this equation, so I do not multiply it by tau here. Sorry. I would put another coefficient, so basically, we start with the same model, xt a1 xt minus tau plus a normal increment. Then delta is xt minus tau, which is a1 minus 1 times xt minus tau plus epsilon. How do I get dt here? This would be actually what we're experiencing at the moment is a very well-known phenomenon that it is not so easy to get from a discrete model, which I did originally with a time step tau. to a continuous time model. So in order to get a continuous time model, there would be a differential of time here. So what I would probably do, I would, this is a coefficient which corresponds to the time tau. So I would need to divide this coefficient by tau, divided by tau, multiply by tau here, and then I would have, instead of a1 minus 1 here, I would have, well, some kind of a1 minus 1 divided by 2, or I would say there would be some b1 coefficient here, something like this. So effectively we get dxt in the continuous time notation is some kind of coefficient b1 xt dt plus dwt, something like this. Now the question is, what we get? Where b1 is, as we see, it is a limit as tau tends to 0 of a1, which generally would depend on tau, minus 1 over tau. What can we say about this equation? Forget for a second about the random part, about the Brownian motion. Just, it's okay to forget about it. If we consider the equation dxt equals to bxt dt, or x dot t equals to b1 xt, then the behavior of this is exponential. So xt is x0 exponent of minus b1 times t. T is greater than or equal to 0. Correct? By solving this very simple differential equation. Now you see that everything depends on the sign of b1. If b1 is greater than 0, then xt tends to 0 as t tends to plus infinity. All right? Okay? And this corresponds to effectively a stationary case. Why does it mean? So this is approximately, I would say, we can say it is a stationary case. Why? It is stationary because eventually the process up to a stochastic perturbation, but I'm only considering a simplified form of the equation, but we would see that it has a tendency to 0 due to the exponential decay of the coefficient. b1 equals to 0. xt is x0. This is already, actually, you can see this is an unstable and non-stationary case. And b1 being less than 0, then we would see xt tending to infinity, plus or minus, depending on the sign of x0, as t tends to plus infinity. This is not only non-stationary, but it is also called exploding. So stationarity occurs only when the process tends to zero as t tends to plus infinity, and the process becomes indistinguishable from zero up to a stochastic perturbation as time increases. So basically, even in this setup, if the stochastic part, the incremental Brownian motion, introduces a perturbation into our process, looks like this. So for example, there was some initial value. The process depends to zero. Now stochastic perturbation introduces a new value, but the process then again tends to zero. Now we get a stochastic perturbation into a negative, but the process again tends to zero, and so on. So in the long run, you can even obtain an analytical distribution for this type of process, and you can really see that it tends to a stationary distribution as t tends to plus infinity. But not in the case when this only happens in the case when B1 is positive. Not in the case when B1 is 0 or B1 is negative. Because we had that B1 is actually A1 of tau minus 1 over tau, limit actually as tau tends to 0, then the stationarity requirement is that because B1 needs to be positive, it means that A1 must be less than 1. That's the stationarity condition. And that's precisely what unit root tests would indeed test. And typically it would happen that if for x you consider the original process and you try to estimate this A1 coefficient, then it appears to be not less than 1. In many cases you get either 1 or even larger than 1 coefficients, and in that case larger than 1 coefficients correspond to just a second, what we have put here, sorry, my apologies. We have, why do we have minus here? X dot is B1, sorry, or other way around. We have, and you didn't tell me, xt is x0 exponent of plus B1t, obviously. And in this case, we need B1 being less than 0 for stationary case, or being equal to 0 or positive for non-stationary. I didn't put a minus here. Okay, sorry. Then B1 is A1 of tau minus 1. We need the coefficient B1 to be negative, and this means that, yes, the final condition is absolutely correct. In order to get it negative, we need A1 being obviously less than 1. If for stationarity, that's now correct. If A1 is greater than or equal to 1, then we have a non-stationary or even exploding process. In many cases, for the original xt, if you model your process, it's not as a Brownian motion anymore, but as an autoregression process, you would get this A1 coefficient to be on the wrong side. So you would get it greater than or equal to 1. But if you consider, for example, that was for xt, but now if you have, for example, the process yt, which is delta xt, and apply a similar test, test to yt, you would get for So you would eventually consider dyt equals to a1 yt dt plus, for example, dwt, something like this. Then you would already get this coefficient to be, sorry, b1 to be negative, and therefore yt becomes stationary. So using first differences is a way to achieve that our process is hopefully stationary, which we can check by estimating the corresponding autoregression coefficient in the simplest case. If for whatever reason the first difference process is non-stationary, then we can take second differences, third differences, and so on until the process becomes stationary. Typically, it is not needed. Normally, first differences are enough to achieve stationarity. Moreover, an interesting thing is sometimes you don't even need first differences. There is a notion of fractional order differences. Imagine not whole order like first, second, third, but fractional order differences. And for example, a difference of the order less than 1, maybe 0.5 or 0.8, would become sufficient in order to achieve stationarity of a process. And in that case, it's better to take fractional order differences. You may wonder, what is a fractional order difference? That is a very important technique which we'll consider in the next lecture. We'll start from that point on. For today, we're done. Any questions, please?
No.
Okay, thank you very much. Thanks a lot.